Hi everyone, in today's video we're going to be talking about how to use integrals to find the volumes of three-dimensional figures. So we're taking a departure here from the area that we've been working on and now actually working with those three-dimensional figures. So you guys got kind of a taste of what this looks like doing your models in class, and so today we're going to walk through how we use integrals to find these volumes. So to do this, there's some area formulas that we're going to need to know. And some of these are pretty basic and straightforward, and some you're probably not as familiar with. So let's go ahead and go through these first. So first one, area of a square with side length s, we know is just area equals s squared. Okay. The next one we're going to talk about is how we find the area of a square if we know the diagonal. Sorry, that's not a great straight line here, but if the diagonal is length d. Well, there's a couple things I need to know here. If I draw on a diagonal, I know what I've created now is a 45, 45, 90 degree triangle. So if my diagonal is d, it means these other two legs of my triangle, and a 45, 45, 90 would be d over the square root of 2. So now, if my side length is d over root 2, I have area equals my side length, d over root 2 squared, which is going to give me d squared over 2. Okay, next one is a semicircle of diameter d. So now, we're all familiar with the formula for the area of a semicircle. So I know that is pi r squared over 2. Now, the only thing I need to do here is I need to get this in terms of the diameter, not the radius. So I know the radius is d over 2, so I'm going to make a substitution here. So I have pi times d over 2 squared over 2, and then we'll go ahead and simplify that. So now I have pi times d squared over 4, sorry that's a little messy, all over 2. So now I'm going to just move that 4 here to the denominator, essentially multiply denominator and numerator by 4. So now I have pi times d squared over 8. Now, for the purposes of when we're integrating, a lot of times I just like to pull a constant out front. So I'm going to rewrite this as area equals pi over 8d squared. I'll box that in because there's a lot going on there. Okay, the next one, we have an equilateral triangle with sides of length s. So I know this whole side length is s. Now, for a triangle, I know I need 1/2 base times height. So I know what the base is, but I have to find this height. Well, when I dropped that perpendicular, that altitude, this was an equilateral triangle. So that meant this angle was 60 degrees, which means by creating this separate triangle, I've created a 30, 60, 90. Now, when I dropped that altitude, that made this side length here s over 2. So s over 2 is the side opposite the 30-degree angle. To get the side opposite the 60, I multiply by root 3. So that tells me that my height here is s root 3 over 2. So now my area is 1/2 the base, which we said was s. Then we said the height was s root 3 over 2. So now I'm going to kind of pull all my constants together. I've got 2 times 2 is going to be 4 in the denominator. So root 3 over 4 times s squared is our formula. Okay, now we have isosceles right triangle with legs of length s. So this is isosceles. These are the same. So now if we just apply our area equals 1/2 base times height, I have 1/2 times s, or 1/2 s squared. Now, the last one, we need our area formula. Now we don't know the lengths of the legs, but I know the hypotenuse is h. But again, if this is isosceles right, I know these two legs are congruent, so what I have is a 45, 45, 90. So if my hypotenuse is h, means my legs are h over root 2. So now I can use area equals 1/2. My base is h over root 2. My height is also h over root 2. So I get my area is equal to root 2 times root 2 is 2, times 2 is 4, so h squared over 4. So these are the 6 area formulas that we'll come up against most often. A lot of you will find that you just memorize these. However, I wanted to show you how to derive them in case on a test or the AP exam you can't remember it. You can always come up with that formula on your own. All right, so now when we're talking about volumes by slicing or volumes by cross-section, you'll kind of hear those things interchangeably. What we know is if we take our 3D solid and we were to slice it, we get the same shape every time. That shape only varies in size depending on the base that it's sitting on. So we're just taking slices of that same shape. So in other words, if we were to add the areas of all those shapes, we would get our 3D solid. So just like what we talked about with area, sometimes we're going to have cross-sections perpendicular to x and sometimes perpendicular to y. So in other words, sometimes we're going to have to integrate with respect to x and sometimes with respect to y. So here's how it's going to look. If our cross-sections are perpendicular to the x-axis, this means we're going to integrate with respect to x. So what we're going to do is we're going to take the integral. Since we're with respect to x, my lower bound is going to be my left x value. My upper bound will be my right x value. And we're going to integrate that area formula from up above. We're going to have that area in terms of x, and then we'll have our dx at the end. Now, sometimes a problem will specify that our cross-sections are perpendicular to the y. So in this case, we're going to integrate with respect to y. And much like with area then, when we integrate with respect to y, now the bounds of our integral have to be y values. So here we're going to have our lower y value. Our upper bound is going to be our upper y value. And now when we integrate, we're going to have the area formula, this time in terms of y, with our dy at the end. Again, as we're going through, I want you to be really checking those integrals. Make sure your variables are all matching and that you're including that dx or dy at the end. All right, so let's go ahead and look at some examples of how this is going to work. So problem number 1, it says the region bounded by the graph of y equals 2x minus x squared. So here's my curve. We already have the graph. And the x-axis is the base of a solid. So really quick, just so I know what I'm working with here, I'm going to kind of just identify that as my base. Now, there's a couple things I'm looking out for. It says for this solid, each cross-section perpendicular to the x-axis. Okay, so I know I'm going with respect to x, right? Since I'm perpendicular to the x-axis, so I better be working all in x's. And now it says each cross-section is an equilateral triangle. So that's telling me what area formula I'm going to be dealing with. And so it's asking us what is the volume of the solid, and we're going to go ahead and use our calculator for this. So here's how I'm going to do this. The first thing I'm going to write down, so you don't have to number your steps, but just to give you an idea of how this process is going to go, we're going to write down our area formula for an equilateral triangle. So we said that area is going to be root 3 over 4 times s squared. Now that I know the area formula, I need to get that area in terms of x. So here's what we're going to do. The idea here is that we're slicing this perpendicular to the x-axis. And each of those slices, each of those segments that I drew, is really the base of an equilateral triangle. If you can imagine a 3D triangle sticking off of your page, this is one of the bases of that triangle. So to get that side length, essentially what I'm going to do, my s is just going to be equal to the top, or let me put this here. So the s is going to be equal to the top of that curve minus the bottom. So we're going to figure out what s is in terms of x. Well, the top is defined by my 2x minus x squared. That's my top. Well, my bottom is just the x-axis, so y equals 0. So my s is just 2x minus x squared. Now that I know what s is in terms of x, I can write my area formula in terms of x. So area in terms of x, I still have root 3 over 4, but now s gets replaced with 2x minus x squared. And then we're going to square that side length. Again, s just got replaced by this value here. The rest of the formula stays the same. So now we have what we need. If we look back here, we said we're going to integrate that area formula in terms of x. So that's what we're going to do now in our step 4. Now when I integrate, I like to pull any constant factors out front. So I'm going to do root 3 over 4 times the integral. Well, here my left x is -1. My right x value is here at 3. And then I'm going to integrate 2x minus x squared dx. And now this says we can use a calculator, so we're going to go ahead and do that. Let's see. All right, so I've got square root of 3 divided by 4. Whoops, let's do this. And then math 9, I'm going to plug in my integral, -1 to 3, 2x minus x squared. And we're going to square that again. I don't want to forget that. I'm going to type in my dx. And I get about 5.312. Okay. All right, let's look at another problem now. So number 2 says the base of a solid is the region enclosed by y equals e to the x. So I've got this curve here. Y equals 4 and the y-axis. So now I'm looking at this region here. Now I have cross-sections that are perpendicular to the y-axis. So now I'm going, my slices look like this. And in this case, what these are the bases of rectangles with heights twice the length of the base. So we'll go ahead and deal with that in a minute. Now, since I'm perpendicular to the y, that means everything needs to be in terms of y. So I'm going to keep that in mind. The first thing I'm going to work with is this area formula. So in general, if I have a rectangle, I know my area is base times height. However, in this case, it says my heights are twice the length of the base. So my base is b, but now my height is 2b, because height is twice the length of the base. So my area formula is 2b squared. Now, I need to figure out what that b is. Since we're going with respect to y, I know b is going to be defined by this distance here. I'm going to take my right curve minus my left curve. Well, now here I have to do a little bit of work. Since y is equal to e to the x, I have to get this solved for x in terms of y. Well, luckily now you guys have had a lot of practice with this. If I take the natural log of both sides, that tells me that x is equal to the natural log of y. So now this curve is just x equals the natural log of y. So my base is natural log of y minus, well here, this is just x equals 0. So minus 0, so my base is the natural log of y. So now my area in terms of y is 2 times my base, which is natural log of y, and we're going to square that. So now all I have to do is take the integral. So I'm going to put my 2 out front, my integral. Now remember, since we're with respect to y, our limits of integration have to be the y value. So my lower y value here is 1, my upper y value is 4, and I'm going to integrate the natural log of y squared dy. And we're going to go ahead back to our calculator. So I have 2 times math 9, the integral from 1 to 4 of, let's see, natural log of x, and I'm going to square that times dx. And I get 5.194. Now, what I would hope is that you guys are actually entering these into your calculator as well along with me. I find that a lot of times errors happen just in the entering of these in the calculator, so I hope we're getting practice with that. All right, one more to go here, and then we are done for today. So the next problem, number 3, says consider the space bounded by y equals x squared, the line x equals 3, and the x-axis. So now in this case, we have to make our graph. And again, I'm just really concerned with getting the basic of idea of what's happening here. So I know x squared is going to look like this, my parabola. Ooh, that's terrible, but we get the idea. The line x equals 3, and the x-axis. So now here's where I have to be really careful. If I'm bounded by, let's see, x squared, the line x equals 3, and the x-axis. So I'm looking at this region here. Okay. Now I have a 3-dimensional solid that's made by making cross-sections perpendicular to y. I wonder if this is supposed to say bounded by the x-axis. Let's see. Okay, so looking at this problem, hopefully you guys caught it before I did. I was working a little too quickly here. This is not the graph that I'm after. And if I read this more carefully, I've got y equals x squared. Now, it didn't say the line y equals 3. It's actually the line x equals 3. So it looks like this. Now this is making more sense. So I have y equals x squared, the line x equals 3, and I'm bounded by the x-axis. So if I look, I have y equals x squared, the line x equals 3, and the x-axis. So this is my region. Now I'm back on track. Okay, so suppose a 3-dimensional solid is made by making cross-sections perpendicular to the y-axis. Okay, so they're going to look like this. So each of those segments in this cape is the diameter of a semicircle. So if you can imagine, this is the diameter of a semicircle that's kind of being raised off the page here. So set up an integral that can be used to find the volume of that solid. So we start with our area formula as always, and we know in this case it's pi over 8 times d squared. Now our diameter here, since we're going perpendicular to y, this is going to be right minus left. Well, let's see, my right was y equals x squared, but since I'm going perpendicular to y, I need to solve this here for x in terms of y. So if I take the square root, I get x equals positive or negative square root of y. Now, since I'm in the first quadrant here, I only have positive values there of x, so it's just going to be square root of y. Now, I think I misspoke a little bit here. Here's where we have to be careful. Now, in our right case here, my right bound is this line x equals 3. So my right is 3. My left bound is my curve, so minus square root of y. Now I can write my area formula in terms of y. I have pi over 8 times d, which is 3 minus root y, and then we have that squared. So now we can integrate. So my volume is going to be equal to the integral. I'm going to put my pi over 8 out front. I have the integral of 3 minus root y squared dy. And now we have to decide on our bounds here. So I know that I'm starting at 0. And then I have to find this upper bound here, my upper y value. So let's go ahead and look at this. What we know is we have, if I clear out here, I have y equals x squared. And then I have the line x equals 3. So what we need to do here is find out when square root of y is equal to 3. So I'm not going to use my calculator for that. I know x equals square root of y, and I want to know when that's equal to 3. Well, that tells me, if I slide this up, if I square both sides, that y is equal to 9. So now I know my upper bound is 9. And now we'll go ahead, in the interest of time here, use our calculator to calculate this. See if I can go the rest of the way without making a mistake here. Pi over 8 times the integral from 0 to 9 of 3 minus the square root of x squared dx is going to give me 5.301. Okay, so that is it for today. As always, thank you for your attention. And obviously, you'll get some time to practice this then when you're back in class on Monday. So I hope you all have a great weekend, and I'll see you when I am back.